We defined energy yesterday as the ability to do work. Now, that doesn't mean that it's doing work right now, but it means that it either is doing work right now or has the potential to do work down the road. In other words, the object is moving and it possesses kinetic energy, or it has the potential to move, so it possesses potential energy. It's stored energy, kind of just waiting in the wings to get the object moving. Now, we talked about kinetic energy yesterday in a little bit more detail than we did potential energy. We said there was an equation that describes kinetic energy, 1/2 mv squared. What did m stand for again? Of course, m stands for mass, right? It's going to be in kilograms. What does v stand for? Yep. Good. It's speed. It's not velocity. It's speed. The units for mass are going to be kilograms. The units for speed are going to be meters per second. And of course, the units for energy, kinetic energy, are going to be joules. Hey, is energy a vector or a scalar? Don't remember? If you don't remember whether it's a vector or a scalar, take a look at it. Okay. How do you know just by looking at this that it's either a vector or a scalar? Okay, it doesn't tell us direction, but how do we know by looking at that equation up on the board right now that it doesn't tell us direction? So you're saying it's a scalar then, right? Kinetic energy is a scalar. You're right. But if you don't remember that, how do you know by looking at this variable, either on the board or on your data sheet, that it's a scalar? Yep.
There's no arrow.
It doesn't have the arrow over top of it, right? That's your little cheat. Right? If you ever asked whether something's a vector or a scalar and you don't remember, look at your data sheet. If it has the vector, it's a vector. If it has a little half arrow, it's a vector. If it doesn't, it's a scalar. Hey, one quick little thing here. It's been a while since we've done this, so I want to come back to this and just do a little example. What if we have to convert kilometers per hour to meters per second? Let's say we got 90 kilometers per hour given to us in a question. We have to convert that to meters per second to put it into my kinetic energy equation. You guys remember how to do that? Because we really haven't done that much this unit, right? This unit's been about forces and accelerations, and every once in a while we may have had to do that, but not very often. Don't make it harder than it has to be. If you want to convert kilometers per hour to meters per second, convert kilometers to meters and convert hours to seconds. Do it one at a time. 90 kilometers is 90,000 meters per hour. 90,000 meters per, well, 1 hour is 3,600 seconds. So it's 90,000 meters divided by 3,600 seconds. I think we need to do that one. I think it ends up being 25 meters per second. And multiply by 1,000, divided by 3,600. Now, the other type of energy was potential energy, stored energy, energy that has the ability to get something moving, the ability to do work, the ability to cause kinetic energy, but it's not kinetic right now. We talked about a bunch of different types of potential energy yesterday. One that we're going to spend quite a bit more time on today. One that we're going to spend some more time on in our last unit this year. And then the rest of them just other kinds of potential energy that you might see in chemistry class or biology class or whatever. What's the main kind that we're going to deal with this unit? In fact, today? It's the energy stored in this board marker right now. Yeah. Good. It's gravitational potential energy. Another kind of potential energy, it's the energy stored in the elastic as I stretch it and let it go. Call it elastic potential, spring potential. There were a couple more types of energy that we talked about yesterday that we don't really focus on in Physics 20, but remember one of them? How many people drove to school this morning? How many people walked to school this morning? One or two people walked? Okay. If you walked to school this morning, you had to get your energy from somewhere. If you drove to school this morning, the energy in the car had to get its energy from somewhere. In both cases, whether you walked or drove your car, there was potential energy converted to kinetic energy. It would have been what kind of potential energy? Yep. Chemical potential energy, right? We talked yesterday about solar energy as well, about nuclear energy as well. Okay, all kinds of energy that ultimately can be harnessed to produce kinetic energy. In other words, all kinds of energy that can be that can ultimately do work. Not doing work right now, like kinetic is, but ultimately can do work. All right. We left you with a couple questions, 3 questions, I guess, for homework last night. Page 303. Any of those 3 questions that we'd like to take a look at here today? All right, if there's no problems with those, we'll move on and talk a little bit more about gravitational potential energy. We say the gravitational potential energy is the energy that's stored. Any kind of potential is stored energy, right? But specifically, gravitational potential is energy that's stored in an object due to its height. The higher something is, the more potential energy that it has. But higher relative to what? We can measure the gravitational potential energy relative to whatever we want. For instance, the gravitational potential energy right now of this board marker relative to the floor is something, okay, because it has potential to fall to the floor. But relative to my hand, the gravitational potential energy of this board marker is 0, because it has no potential to fall to my hand. It's already at my hand. We have to pick a reference point to define potential energy relative to. That potential energy can be defined relative to the ground, relative to the floor, relative to a tabletop, relative to your hand, relative to whatever you want, as long as you specify what your frame of reference is. Usually, it ends up being relative to the floor or to the ground. So how do we calculate the gravitational potential energy? This is an equation that you've seen before in Science 10 as well. If gravitational potential energy is dependent upon height, then height is going to appear in the equation, right? The bigger the height, the bigger the potential energy. What else does it depend upon? I think we had briefly addressed this yesterday, didn't we? It's also dependent upon how heavy the object is, right? If you have a heavy object and you drop it, it's going to do more damage than if you have a light object, right? It does more work. So it's also dependent upon the mass. But finally, it's dependent upon how strong gravity is. Okay, if you're at the top of Mount Everest, the potential energy of an object a meter above the ground is slightly less than if you're in Vancouver at sea level. So gravity matters. Mass is measured in kilograms, height is measured in meters, relative to something, relative to the floor, relative to the tabletop, whatever. And G is usually for us going to be 9.81 meters per second squared, but could be something else depending upon where the location is. Okay, what point on Earth it is, or what planet that you happen to be on. Let's do a problem here. 6.3 on 298. So 6.14, figure 6.14 shows a toy car track set up on a tabletop. We want to know the gravitational potential energy of the car relative to the floor. Now remember, we can define the potential energy relative to whatever we want, relative to the floor, relative to the tabletop, relative to the top of the track. They're specifying this time that we want the potential energy relative to the floor. If that's the case, then we need to use the height above the floor. If we wanted to find the potential energy relative to the tabletop, then we would simply use the height above the tabletop. Let's do question A now. EP is equal to mgh. The mass here is 0.0250 kilograms. G is, of course, 9.81 meters per second squared. And the height is the height from the floor to where the car is, 2.15 meters. But remember, if you wanted to find the potential energy relative to the tabletop, we would only use this height, the height above the tabletop. Okay. Usually, you get to pick what your frame of reference is. This time, they tell you that they want you to do it relative to the floor. Fraser, what do you get? 0.537. And it is 3 significant figures. Yeah, there we go. All right. B, oh, this is a bit different. What's the change in gravitational potential energy of the car when it arrives at the bottom of the hill? Change. What do you think of when you hear the word change? We don't like change. It's not like funny angles, though. People just don't like change, but that's okay. It's not a big deal in this one. Yeah. Yeah, delta, right? Final minus initial. Right, if you want to find the change in potential energy, you've already got the initial energy right here. Let's get the final energy and let's subtract them. So let's say EP final is MGH. That's going to be 0.0250 times 9.81 times the final height of 0.950. Now, we said that you can pick whatever frame of reference you want, whatever reference point that you want here. If we're going with the reference point of the floor in question A, then we got to go with the same reference point in question B, right? I said you can pick whatever you want, but only to a certain degree. If you're going to subtract two numbers, you've got to use the same reference point for both of them. So let's get that number. Who's got the value of EP final there? 0.025 times 9.81 times 0.95. Anybody else get that? 0.233? Thank you. Now, if we're finding the change, remember, that's not our final answer. Be careful. Hey, if this was a multiple choice question, guess what one of the options would be? 0.233. Some of you would get that and say, oh, that must be the right answer because I got an answer that's one of my options, but you're not finished yet. The change in potential energy is the final minus the initial. So it's going to be 0.233 joules minus the initial energy of 0.537 joules. And that's going to give us energy is a scalar. How can we have a negative value of delta E if it's a scalar? Doesn't negative mean left or down or something like that? But energy is a scalar. So what does that mean? What does a negative mean for us if it doesn't mean left or down? Which it can't because it's a scalar. The negative delta E means it's a loss of energy, right? We had 0.5, now we got 0.2, we lost 0.3, or my change is negative 0.304 joules. All right, take a look at those three questions, please, on page 298.